Good morning, everyone. I'm Shenghui Cheng from Westlake University. Welcome to this international lecture from Professor Klaus Mueller. First thing is very important. So everyone who are interested in ask some questions, please scan this QR code to get the WeChat group, and then you can post your question there. Okay, this is the audience group. Okay. Now I will introduce Professor Klaus Mueller for his talk, New World Embedding, Adding the Human in the Loop. Okay, Klaus Mueller received a PhD in computer science from the Ohio State University. He is currently a professor in computer science department at Brook University, and he is also a senior scientist at the computational science initiative at Brookhaven National Lab. His current research interests are visual analytics, data science, and explainable AI. He won the U.S. National Science Foundation Early Career Award and the Stony Channel Award for excellence in scholarship and creative activity, and the Meritorious Service Certificate and the Golden Core Award of the IEEE Computer Society. To date, he has authored more than 200 peer-reviewed journals, which have been cited more than 11,000 times. Klaus currently serves as editor-in-chief of IEEE Transaction on Visualization and Computer Graphics, and a senior member of the IEEE. Okay, let's welcome Professor Mueller for his talk.
Okay, thanks a lot, Shenghui. You got it exactly right. So I'll share my screen now, I guess. Welcome, everyone. Thanks for having me. And you'll learn a lot about neural world embeddings if you don't already know it. But yeah, I also tell you how to add the human into the loop, which you might not know. So just see if I can collapse this. Okay. Okay. So let's first start off with explaining actually what is a word embedding for those who don't know. So a word embedding basically is a mapping where words associated with similar concepts located into close neighborhoods. So here's an example of a word embedding. So you'll see, like, for example, you'll see voices and sounds are here. These are all words associated with voices and sounds. Here are some words about critical communication, like conversation, thought, communicate, thinking. Juvenile is here, kid and youngster. Education is here, college, elementary, and grade. And then you also notice some things, there's like these months, but they're like disjoint, right? There's like some months are here and some months are here. So that's interesting. And then also here, decade, hour, minute is here, and month, day, and year is here, although they're both so related to time, right? So the word embeddings aren't perfect, right? So that's why you want the human the human in the loop, right? Because the human has to, sometimes word embeddings just don't know all the layout because they learn from data, and the data may be incomplete, or maybe they're not consistent or ambiguous. And then the word embedding just can't make sense out of it because it's just a robot, not the real human. So a human can rectify this. So I'll show you some examples in how humans can assist the word embedding, but of course a lot more than that. But I'll just want to make you aware of this, okay? So what is a neural word embedding, right? Because it's a neural word embedding, because these word embeddings are learned using a neural network, okay? Like a very shallow one, not like a big neural network, TensorFlow, or anything like this. It's a very, very shallow one. So basically, it just consists of one hidden layer, which is in the middle here, of 300. Well, you can have more neurons than that, but 300 neurons are oftentimes enough. So you have 300 neurons here, which is the hidden layer. And then you'll have this output layer, okay? This just depends how many words are in your corpus, right? And how many words you want to resolve. So let's say we have 10,000 of them. Okay, then you use this one hot encoding here on the input, where only one word at a time will appear. Okay, so let's talk about this some more. So basically, your corpus is going to be like lots of text that has all kinds of words. Usually, people use a Wikipedia collection or some other very large corpus of text that's very diverse. So I'll just give you a few of them. And then in 5 words at a time. So the car cruises the road, a driver steers his car, a road full of cars. Do you have car insurance? A desk is in a room. Okay, these are 5-letter sentences. And so I highlighted car because we're gonna try to resolve the word car. So let's say, we'll have a one hot encoding here, and we'll turn on the word car, which is at one particular position in this input vector. It's only one is always on, like either car, here might be and, here might be wheel, whatever it is, like we turn on car. And then we'll basically pipe it through this network. And at the end, we'll compute, we'll just let it go through, and these weights are set, could be in the beginning or arbitrarily set. And we'll figure out, like, what is the likelihood of another word being close to the word car, okay? Because we basically compare our entire text corpus and make sure that all the words that are close to car in many of those instances get a high probability, and the words that are not close to car in most instances get a low probability. We'll just keep tuning the weights until that happens. Okay, so insurance gets a probability of 4.6, driver gets a probability of 4.6, desk gets a very low probability, and road gets a very high probability. Okay, because there are probably more text snippets with that have road and cars close together. So basically, we train this network in terms of the context of the word that has of the word that is currently under investigation. So we'll present all of these different words one at a time and try to tune the weights in such a way that these probabilities work out correctly. Okay, and we'll just keep doing this until it's fully trained. Okay, so now once we have trained this network, we have the weights for all these layers here. Then we'll basically what we'll do, we'll keep the hidden layer weights. We don't keep anything else. We'll keep the hidden layer weights. Those weights here, we keep them because so we'll have basically 300 neurons and 10,000 words. So each word basically has 300 features, right? All those connections from those different neurons. Okay, and then what enables us now, we can compute similarities from this, right? So we can say when there's a word car and a word wheel or a word driver, they probably have very similar features, very similar weights, right? Very similar weights, because they oftentimes appear together, right? So when there's a car, the probability for driver is very high, and when there's a driver, the probability for car is very high. So they turn out to have very similar word vectors. These vectors are very similar. So whenever I compute the dot product of those two vectors, let's say for ants and for car, or for driver and for car, or for wheel and for car, I'll get a certain product out of it, right? Then I can compute a distance matrix out of this. For each word pair, I compute a distance. Okay. So once I have this distance matrix, I can take any kind of embedding, two-dimensional embedding method like MDS, TSNE, UMAP, whatever it is, or PCA even, and create this sort of mapping here that will tell us that groups words that are close together in terms of context also map close together in this picture. Okay, so this is basically how I'm going to get from a word corpus to an embedding. Okay, this is what's called the neural embedding. The neural embedding is really the 300, is the higher dimensional space, and then this embedding that I show here is the visualization of it. Okay, so now this is basically all about this word embedding. So now implementations, there's many implementations of this. Word2Vec is probably the most common. Klaus is another one that's pretty common. And all you really do is you get this skipgram and some other stuff that comes along with it, and you can just take your own text corpus and train it. Okay, just take your own text corpus, or use a pre-trained one, for example, one that's pre-trained by Wikipedia already. Right, then you already have your weight vectors and everything. The only problem with that is there's an inherent problem is that there's a conflation of word sense, because every word only has only one location, right? So it could be the word jaguar, for example, right? The word jaguar is a car and also a cat, right? So there's these kinds of, then the mapping is not perfectly accurate, right? Because a car could be mapped, the jaguar could be mapped to the cars, but might also be mapped to the cats, right? To the wild cats. So this is basically, there's a little bit of a problem. So now there's new methods, like newer methods like BERT and Elmo and all kinds of methods like this. They're trained on a wider sentence level context. They can resolve these kinds of problems with this conflation of word sense, so you can do this. But, they're somewhat more complex than Word2Vec. They use transformers oftentimes. So for our work, usually Word2Vec works just fine. Our embedding is not that high, it doesn't have that high of a demand that we need big machinery like BERT. So we use Word2Vec most of the work, but we could also use BERT or something like this. So let's talk a little bit about some applications, okay, that we've done with these word embeddings. So one of them is semantic subspace clustering for high-dimensional data, and we'll talk about this first. Then we'll also did some work on construction of semantic data-driven high attribute hierarchies. And then I'll go back and actually show you an application that we've done that helps people to discover biases in word embeddings, right? These word embeddings might have biases because when you train the word embeddings, you train them with text corpuses that might have biases in them, right? There may be overrepresentations of certain concept, underrepresentation of other concept. There may be concepts are mentioned often together, which shouldn't be mentioned together. We'll see about this, right? So uncovering these biases is very important because these word embeddings are often used to train machine learning classifiers, right? If there's bias in those word embeddings, then there's going to be bias in the classification, and that can have pretty bad consequences. So these works that I'm going to show you, they were all done in the VI lab, in the Visual Analytics and Imaging lab, which is my lab, by Salman Mahmood, who graduated recently and is now at Google. And Bhavya Gai and Naimul Haq are still PhD students, but also pretty advanced at this point. So let's talk about this semantic clustering. So first of all, high-dimensional data, right? We're trying to basically cluster high-dimensional data. So what is high-dimensional data? High-dimensional database is all the data that have a lot of variables or attributes. It's basically a spreadsheet with nominal and categorical data and a lot of data points on the as rows, right? So this basically is a high-dimensional data set. This still happens to be a high-dimensional data set of cars. So you want to visualize these high-dimensional data. So what you often use is some sort of projection into two-dimensional space, because 2 dimensions is what you need to visualize it, right? You cannot really see in 5D or 6D. You need to somehow project it to 2D so you can actually see what's going on in your data, right? So I show here a few projections, like biplot is one. Biplot is pretty nice because it sort of shows clusters, and at the same time it also shows the dimensions that sort of are relevant for these clusters. So it gives you a really good context for what the cluster is all about. Then TSNE, T-distributed stochastic nearest neighborhood embedding, is a more modern technique. What it works more on it's more like probabilistic, that it tries to sort of bring together points that are sort of more closely connected in high-dimensional space and makes these clusters out of them. Okay, that's it loses the dimensions though. In biplots, you can still see the attributes. In TSNE, you don't really know anymore what these clusters are really all about, right? The context is missing from that. Then there's also UMAP, which is a little more modern. It preserves global structure more. So all of these things are basically methods that you can use to project your high-dimensional data into 2D. But all of the problem with all of these methods really is if you have too many dimensions in the data that you use for these projections, right? Whenever, when you take this n by n matrix or n by n matrix, try to compress it into 2 by n matrix, then the more dimensions you have in this process of collapsing that, you may lose a lot of fine detail of the projections. Okay, because there's too many dimensions competing together, and they all try to sort of get a word in the projection, and then when you do this, it's losing a lot of detail because it becomes too crowded, right? Over constrained. So let's talk a little bit about this, right? Like what you can get when you reduce the number of dimensions before you project. Okay, so you wanna think of a high dimensional data set as an ecosystem of subspace clusters, right? There's like a cluster here, there's a cluster here, and a cluster here. Remember the word embeddings that I showed you? There may be the houses would be there, and the utilities would be somewhere else, and the education might be a different subspace. So if you have these subspaces, which are usually just very sort of themes in the data, right? Which are sort of isolated themes in the data that are sort of within themselves is a small theme, and that there's an ecosystem of many themes, like a book of themes. Then actually the subspace cluster has a much smaller number of attributes that are needed to describe it than the entire data set, because the theme is usually very, very specialized. Okay, so by subspace clustering, you can actually significantly reduce the data dimensionality. So what's the subspace? Okay, so you may wonder what it is, right? So think about this three-dimensional data set here. Okay, there's a green, there's a purple, there's a red, and there's a blue, light blue cluster, or like a cluster of data, and they're overlapping, as you can see, right? So if you project it into A and B, you'll see that this green, this red one, nicely isolated with one another, right? Really nicely isolated. So now you really can see the shape and the detail of this red and this green cluster. While meanwhile, the purple and the light blue, they're sort of mingled together. I can't really see anything, but you can really see what they really are about, right? Now, if you use dimension B and C, which is another subspace, you'll see that the purple and the blue, the light blue, nicely isolated one another, but the green and the red kind of look like a Christmas tree, right, with ornaments, but they're basically mingled together and really can't really ping them apart. Now, A and B, A and C here on the right-hand side, all of them are sort of preserved, but unfortunately they're all overlapping, right? So you can't really see them all by themselves, right? They're always crisscrossing one another, right? So basically, subspace B, like this middle subspace, it can isolate two clusters, and the first one isolates some other clusters, right? So these are like independent subspaces, basically. Okay, by using this, you can nicely isolate some structures, but you lose other structures. Okay, so let's talk more about this, right? So we did some experiments. This was like a while ago in 2014, where my student Bing Wang and I, we basically went and did some subspace clustering with a somewhat primitive method, and we took a 19-dimensional data set, and we found 5 clusters in that. Okay, and we found out 19 dimensions. We found out each of these clusters that we found actually only really had 3 to 5 dimensions each, right? So they did 85% reduction, right? So now, basically, by just isolating these substructures in the data, I could reduce dimensionality of each of these by themselves by 85%, right? So which is pretty good, right? So now it's also easily explained, right? If you have something that you need only 3 dimensions to explain, it's pretty easy to do, right? But if you have like 19 dimensions, it's kind of hard to really figure out what it really is about, right? What is high and what is low, right? So that's basically, with a simple method like PCA, we could already do that. Okay, so now to show you what these clusters are all about, so you actually, when you look at these different profiles, dimension profiles of these clusters, this are the different principal component vector and how it is where these clusters were expressed. You'll see that each of these clusters are really different. Each of the clusters has a very different constellations in this first principal component vector. So so they're very unique. So they're not like subspace 1 and 2, 5 have a little bit similar attribute set, but everybody else has a very different attribute set. So they're very different. They have very different constellations, very different descriptors all by themselves, which is good, right? So now you have these 5 different these different clusters, right? They each of them, one of them is that, one of them is this, right? They can be explained by themselves, right? And can put in a list. So it's much better way to describe a data set than if you don't do that. It's okay. So now subspace clustering is actually a pretty well researched topic, right? So there has been actually research for like 20 years. And you know, it's still hard. It's still hard. So there's a lot of research done, but still people, it's just really hard to do. Okay. So there's like these very famous algorithms called click. Another one is called surfing. Okay. Surfing is basically a bottom-up method. It starts from zero, from no dimension at all, and starts to expand the space, the subspace cluster with a quality metric. So it will basically it will make a new subspace and then grow them out with more dimensions. Like it's a kind of a greedy method, right? So like you have a subspace and then you say, okay, if I took that more dimension, would my density still be the same, or would my density be diluted, right? As you add more dimensions to a subspace, usually what happens to those points, they sort of become less dense, right? Because as you add dimensions, points get spread apart from one another, and in the end, they get so apart that you don't really recognize a very consistent cluster anymore. So, and that's when you usually stop with it. And then you take another subspace and start to expand that one. But what the problem with that is, since it's such a greedy method, you'll see on the right-hand side here, there can be an amazing number of subspaces. Like just this Filipino income and exponential data set, I think it has 60 dimensions or so, has 2,000 subspaces with greater than 3 dimensions. Okay, you know that if you want to explore all of them, you know, you want to look at all of these subspaces, which sometimes are not that much different, right? But still different enough that you can't decide which one is more important. So it's a pretty hard topic to really figure out, to like just to look at these subspaces and to really explore them, right? Because there are just so many of them. So this is essentially the problem with all these automated algorithms, right? That when you just rely on data only, you just can't, you know, you just get stuck with all these different descriptors with these different subspaces that are really hard to overview. Okay, so basically this becomes the subspace explosion, right? There's all kinds of, these are all papers from, all images from papers about subspace exploration. Okay, they all end up with lots of subspaces, no matter what you do. Okay, so here, for example, is one. Here, each of these yellow balls is basically a different subspace. I mean, there's no way you can even appreciate what they are, what they're like, and where they're different, right? So we came up with this method where we said, okay, you know, let's look at this semantics of the subspace and see if we can like figure out a better method in sort of overcoming this explosion of subspace evolution, right? So we call that our method semantic subspace clustering. Okay, so you will guess like semantic means will probably involve word embeddings, because the semantic is given by the words, by the attributes, right? That's where the semantics come from. So let me explain this algorithm in detail. Okay, so let me just drink something. So in the next, this sort of figure I'm going to build up is we'll encode algorithms, these wheels here, and the data is going to be this disk, and analyst, where the human is in a loop, is going to be this figure here. So we're going to start out with just a regular word embedding. So we'll use like general text and domain text, right? Because we're going to build, we want to make sure we cover the domain as well, right? This data set might be from the medical domain or from the law domain, which might not be in a general Wikipedia corpus. So we'll add that as well. So we'll have this general text here and this domain text, and we're going to create a word embedding using Word2Vec or GLOF or something like this, or even Burp, right? And then we'll also need some attributes, right? The attribute labels, we'll use them too, okay? Because this is the particular words we really want to have in the word embedding also, right? And sometimes when attributes aren't like that popular, maybe they're even specialty terms that are not known in the general text and domain text, we'll have each, but also to resolve some conflation of problems, right? To make sure that I really catch the meaning of this attribute, I'll provide some attribute meta text, like some descriptive text that goes with the attribute. Like for example, Jaguar. Like let's say my attribute is Jaguar. Then I'll say like, okay, this is a cat, right? The Jaguar is a black cat, or something like this. Some more explanation about this attribute. And I put all this together and create this word embedding. Okay, out of it. Okay, so now I have this word embedding. Then what I'm going to do, I'm going to filter it, because I don't want to have all these words, because this could be millions of words, right? I'm not going to use them, right? I'm only going to filter out the words that are actually in my attributes themselves, right? Because I want to create a word embedding that has the attributes only, right? Because I'm going to work with the attributes of my data set, right? Not anything else. So I'm going to filter them out, right? I'm going to only filter them, and I'm creating an attribute word embedding, which basically inherits the placement learned from the word embedding, right? Using this word embedding learning. I'm going to have the placement of them, but I don't have all that clutter from all these other words that I'm not interested in, right? So now I have the attribute word embedding. And then remember what I told you, sometimes these word embeddings are imperfect. You know, there's sometimes, because there might not be enough information, and there might be overemphasis of certain aspects, things like this. So you'll always have a human in the loop, and the human will basically interact with this word embedding and move things around a little bit. And whatever comes out of this, we call that the conceptual attribute grouping. Okay, so now we got this attribute grouping. Okay, then from the attribute grouping, I can start projecting things into the semantic data subspaces. I can create these projections of my data set into these subspaces that are defined by these attribute groupings. Okay, and then I have these subspaces. I can do some brushing there, right? I can highlight some points and de-emphasize other points, and I can take these and then reproject them into a different subspace. You know, you'll see examples of this in a minute. And then I can also then expand out the subspace that I found, right? With this algorithm like surfing, this automated subspace composition methods, right? I can, and then augment those semantic data subspace I found with other attributes that might be unrelated to the theme of the subspace, but might be very important, might be very interesting to look at. Okay, so basically, this is my whole system. You know, so let me show you like how this works. So let's say I use this Filipino income and expenditures data set here, which has, I think it has 60 attributes, something like this, or 46, I forget now. And I created this word embedding from it, right? This is basically this top part here, okay? Basically, this is the attribute word embedding that I have here, okay? So already have filtered out all the words, all the other words in my corpus, all gone. The only thing that's left are the actual attributes from the Filipino income and expenditures data set, mapped correctly using the semantics they have with the knowledge of the world, basically. And then I already clustered it a little bit, right? I used some clustering method and clustered it. And I found out, so really clearly up here, the red, you know, are all the foods, basically, vegetables, food, meat, tobacco, you know, fish, alcohol. All of these are sort of food attributes. Then utilities are here. Utilities are here. Where are they? The electricity, agricultural indicator are here. Then electronics are down here on the lower left corner. Transport is the yellow ones. Motorcycle, car. Appliances are just above. Stove, refrigerator, washing machine. You know, and then on the right hand side is housing and income things, and family. Okay, family is here on the lower right. Okay, so you can see, right? I can really see classes or themes of attributes nicely expressed close by, right? Just by embedding, automatically comes automatically. Don't have to do anything, right? And now basically this becomes like basically I could form a subspace out of this. Like if I just want to look at this kind of aspect of electronics, I can just project my data into electronics subspace. Or I can, if I want to see the aspect of income and so on, right? I can take it into this income subspace. Or I can, if I want to see the aspect of food, I can project into this attribute, into these subspace attributes, right? And I get a really concise representation, right? That is not disturbed by other themes. Okay, so let me show you like how this works out. So this is our semantic subspace explorer interface. That's what it actually looks like. And so on the left hand side, we'll see this embedding, word embedding. On the top, you know, there's the there's like on the top here, you can define certain clusters. Already here, I defined 3 clusters, one in magenta, one in blue, and one in yellow. And I can make them more or less opaque. We'll see in a second where this comes handy. And B is the scree plot, because I'm going to use a biplot. And scree plot basically just because this is a PCA projection, okay, PCA projection. So PCA is very sensitive to the number of PCA is very sensitive to the number of relevant attributes, right? So my plot isn't going to be very accurate if there's a lot of dimensions, to significant dimensions of my PCA embedding. Okay, so I'll try to make sure that the scree plot that tells me how many relevant PCA vectors there were for a particular cluster, try to make sure that it falls off nicely. Okay. Then on the right-hand side, I see different subspaces, right? The data projected in different subspaces. They're not labeled yet, so we're going to label them in a second. Okay. So this is the oval interface. Okay. Word embedding, project shift view in a particular subspace, scree plot here, different other subspace that can pull in, and so on. Right. So let's talk about how I would start out. Right. The first thing I would do basically is I would look at this embedding, and I would look at it a little bit and say, you know, let's see if there's anything that isn't quite right. Okay, because the human has to be in a loop. The human has to make it a little better, right? This is basically a first estimate, but you know, it can be refined a little bit just by, because sometimes, as I said before, the data, that the corpus might not be perfect, might be, you know, for example, house rental value, right? When you look at this attribute house rental value, which we use a word movers distance to lay this out, right? Because word movers distance can take care of multi-term attributes, right? So now when you look at house rental value, this could be value has something to do with income, right? Something to do with money, but house has something to do with building, right? With house, right? No wonder it's like in the middle, right? So we want to bring it up here, okay? And we want to also bring up the total employed. We want to bring it up here because we want it to be all related to value, not so much to house. Okay, then family, and here, and then we bring this up down here. The family, bring it down here to where all the other family items are. Then we'll take this restaurant, move it over here. So it's by where the special occasions are. Right, so it's basically a little bit in the eye of the human, what the eye of human thinks is the best. You know, that's where the human in loop is needed. And then once we've done this, we go on the right-hand side and we cluster it with just a regular clustering algorithm. Okay, and so now we have, and then we can color it by the cluster. Okay, so it's clustered and colored. So now we have these themes established. Okay, now we have the themes established. Now we can go on and project something into these themes. Okay, we can say, okay, let's take all the data points and project it into the expenses on food, right? This is all the foods, right? The alcohol, meat, vegetable, food, tobacco, bread, cereals, rice, and crop, right? These are all these food up here. Okay, so we trucked all the data points in here, and we find out this is interesting. You know, now you project them out, you learn that there's like actually 2 different kinds of group of attributes, right? This is a biplot. That basically a biplot is basically the points projected into the first dimension of the PCA of the PCA transform, right? And then also projecting the attribute axes into it, right? Basically, all of these projection values are basically the first are in the PCA vector the component value of the attribute. Okay, so we basically project that into this space as well. So now this is like a typical biplot, okay, as very well described in literature. So what's nice about this interesting here is basically we see crop, rice, and bread, sort of attributes that are very similar. And then these other guys are all together, but they're dissimilar from this. So when we look at this, we all know fruit and tobacco and fish, they're sort of luxurious foods, right? They don't really need them, you know, but crop, bread and cereals and rice, somehow in Filipino culture, these seem to be very common together, right? According to the data that we collected for the family, because they're Filipino family, right? So we call them the basic foods because, you know, because we know that, right? Because crop, bread, and rice are basic staples of the Filipino diet, right? And the other ones are the sort of more luxurious staples. And let's say, okay, any household, all the households that mostly consume these kind of basic staples, we'll just brush them in a certain color, like magenta, for example, and then group them together basically as a cluster, as a subcluster. So now the human just does this, right? The human, so we as a user, we decide to do that. So now we've done that. So now let's see, okay, so this is the food of the more basic people that are, the basic Filipino that eat the basic staples. Let's see how they do in other subspaces, for example, in utilities. So what kind of utilities do they own, right? So let's look at this, right? So here are like these magenta points again. And here the other points are still there, right? But we've used this transparency feature. Remember what I told you? You can color the clusters. You can make the points less opaque, so they're fading away a little bit. So I'm trying to emphasize those magenta basic staple Filipino population group and de-emphasize everybody else, right? The ones that consume luxurious food, the ones that are not basic. So basically now I'm bringing out these basic people. And I learned, well, they don't really spend a lot of money on utilities. They're more like here at the origin, right? Or even at the less, right? But they do spend some more money on medical care and special occasions for some reason. But, we also learned from this that medical care and special occasions are very different from other utilities, housing, transportation. So somehow medical care takes a very different sort of rank among those attributes in the Filipino, maybe also in the American or Chinese culture. I don't know that because I don't have the data, but the Filipino definitely, medical care sort of, people tend to spend money on medical care. They might not spend money on housing or transportation or education. Medical care everybody needs. A special occasion, maybe wedding, everyone wants to spend nicely on weddings, I don't know. So in any case, so let's color all the high spenders. Okay, I don't show this here. Let's take all the guys that spend a lot of money, all the people that are sort of not in the center here, that are further out along these dimensions. Let's color them yellow. Okay, call them the high spenders. Okay, so now we got the high spenders here, and let's see what electronics, let's project them into the electronics own subspace and see how they do there. Okay, so we find out, well, the high spenders, as expected, they also spend a lot on electronics, computers, air conditioners, and so on, right? Cell phones. While the basic staples, they don't really own much, right? We expect that they probably don't have money, right? So they don't buy computers, air conditioners, and so on, right? But then when you project them into the housing subspace, we learn, they also tend to live in smaller houses, but the house age they live in older or newer houses. That doesn't matter so much. Okay, so we know. So by just taking these sort of labeled points that are labeled in some particular theme and then see how they behave in a different theme can give you some interesting idea. So let's go out and come up with sort of a basic message. Like let's look at the family's theme, right? So how do they behave in a family theme? We'll find out the yellow high spenders. They seem to have more of an older family, right? The head age is here, down here, right? That they seem to have a higher head of the family age. And the basic staples, they are pretty much everything. Okay. So what we can sort of say from this, after we've sort of explored this in this sort of sequential fashion, we can say that basic in Filipino families, rice, bread, cereal, and crops make up a major portion of the food consumption in those households with less economic resources, right? So we can basically say that. So this could give you some, it could give you some help with advertising, for example, or cultural or planning of subsidies, or label planning, what stores do you put where, right? So this can all give you very interesting information for all kinds of purposes, right? By knowing that, how they behave in different themes, right? You can get a lot of knowledge out of this. And it's sort of in a structured way, in sort of a storytelling way. You go from one theme to another theme, from another theme, one by one, right? You can sort of start to learn, start to know them, get to know them, right? How they behave. So let's go and do more like this. But let's discover some interesting things outside the box, right? Let's say, how can we, let's say, what would like surfing, what would surfing do, which is a subspace clustering algorithm that is unsupervised, right? You just basically, it will just try to expand this expenses and utilities subspace into the most promising dimension that is now promising from the data point of view, right? Because that basically turns out it still can preserve density, right? Which is basically the surfing's quality metric, right? To preserve the density of the clusters, right? Once it's not dense anymore, it will not add this dimension, right? So it decided to add electricity. Okay, so electricity, obviously, since it's not from the theme, it's sort of goes in a different direction than everybody else. But we also very interesting, what we learn is now that the households, there is some certain households, it found like a new cluster. There is households that don't use any electricity at all, right? That's interesting, right? Before we didn't see this because it was not the right projection, but now we know. Now we see that, right? So, now because we added electricity, and this is on the other side of electricity, negative, right? So it's basically, these are the households that don't use electricity. So let's see who they are, right? So let's take them and color them in yellow, okay? Brush them in yellow and see how they behave in this other subspace, which is the utility, the electronic subspace. Okay, so now we learn from that, right? We learn from that in the electronic subspace. These electricity-less households, they really don't use electronics because they're electricity-less, but they use cell phones. Okay, they use cell phones. So we can actually see now that even though people that actually don't use electricity at all, right, they still use cell phones, because cell phone is sort of it's a basic staple of nowadays, of the today world, right? You need to have a cell phone. It's something that you need by all means, right? It's not just it's not a luxury anymore, like a computer or an air conditioner or a landline. It is something you just need to survive, right? So even though they don't have any electricity and they live like really on the most basic terms, they still have cell phones, right? So you still can see that most of them have cell phones. So it's a very interesting finding, right? So this is just a pipeline that you can really use to sort of explore your data one by one and add things in a sort of a storytelling theme, which is much better than being faced with 2011 subspaces where you don't know where to go, right? So now you have a clear sort of structure, a clear sort of line that you can walk and start learning about your data, right? Without having to look at 2011 subspaces that are completely unstructured and unsorted, right? So by just adding this sort of semantics into the subspace clustering algorithms can give you some guidance, and that's actually what we showed in this work. Okay, so I have some video, but I want to skip over it because I don't want to spend the time. I think you got the idea how this all works. So let's go on to another work that Salman Mahmoud also did. This was a work that was the paper before that one, which is related to this, which is called taxonomizer. Okay, which is sort of using a similar idea of word embedding, okay, but for different purpose. So oftentimes when you have like a large attribute space, right, like hundreds of attributes, you don't really know. You want to create some sort of ontology, some sort of taxonomy, some sort of organization to those attributes where similar attributes are sort of themed together, and that you can sort of expand or collapse on your will, right? So for example, if you have area, you can expand it out to demographic locality in city, or you have school, or demographic, you can bring it out into athletic, housing, population, income, right? So basically you can sort of start expanding it out and then collapsing it, and you can sort of look at these different attributes in like a smaller dimensional space, right? To sort of examine them, how they work. Okay, so basically come up with like a low dimensional embedding just based on these particular subspace again here. This is just now creating this hierarchy. So this taxonomizer that was at the root of this, I want to explain it to you a little bit. So basically what it will do, it will make two embeddings one is a semantic embedding that is just like before, right? Done with word embedding. And another one is the correlation embedding, which is the data embedding, right? It basically uses the data. It tries to, it uses the attributes, but in terms of the similarity of the data that the attributes carry, okay? So it's like the vector, like the normal data matrix correlation layout. That is what usually, this is the semantic layout of the attributes done with word direct. And this is the correlation embedding that is the typical thing you have to do. And then you basically take these together and which I'll show you in a second by an example, and you sort of jointly build an attribute hierarchy where you can make the attribute more weighted towards the semantics or more weighted towards the data similarity, attribute similarity in terms of the data, using this, what is called cophonetic correlation plot. Okay, so here you can take this left or right and make the hierarchy more semantic or make it more data centric. Okay, and then you can label it. Okay, with this you can label these interior nodes, which I will show you in a second. Okay, so this is the overall interface of this taxonomizer. Okay, so let me like explain how this works. Okay, so so I start out with these two spaces, right? So this space up here, cosine distance space, NMDS, non-metric multidimensional scaling layout, and another one is here this data space, which is based on correlation distance. So here's cosine distance in the word embedding space, correlation distance in the data space, in the attribute space determined by the data. Okay, so I have these two layouts. And I construct two hierarchies from that. Okay, two hierarchies. One I construct by two dendrograms based on just clustering, right? Just based on clustering. Okay, so hierarchical clustering. Now I'll see already a few things here. Okay, I have to put my glasses on. So I see this is for a Kings County housing data set. So so I get some structures here already. Bedrooms and bathrooms all together, collapsed here, and attic and basement and restaurant are here, collapsed here, and so on. So you get a little structure hierarchy here. And the data space is more like different actually. Landmark and restaurant go together, and then transportation, school go together, and then they go together a different node. Hospital joins here. So so these hierarchies are not the same. And with this thing here, this cophonetic distance slider, I can now set my preferences. Okay. And depending on that, there's always an optimum, right? There's like an optimum where, the data space, this basically tells me what it does. It computes how well this hierarchy matches the particular distance relationships in the layout itself, right? So that's basically what it does, right? When this hierarchy is very different than the hierarchy that is imposed by this particular embedding, then this curve will go down, and then the other one usually goes up, right? And there's sort of a sweet spot here where both of them sort of are not optimal, but both of them sort of they meet together, right? Because two curves always must meet, right? So when one goes down, one goes up, right? So this is basically, it happens to be the optimum. That just doesn't mean it's the optimum. It just means they're equal. They have an equal cophonetic distance. Okay, and then you can choose anywhere you like, right? Interactively, and then it basically creates this sort of joint hierarchy on the right hand side, okay, which is a joint. It's basically a weighted. It's a weighting of the two hierarchies. It's actually a weighting of the two spaces. The distance relation of the two spaces combined together makes this conjoint dendrogram that is now basically trading off these two different accuracies. Okay, so that's basically the idea. Okay, for now, right now, everything is pretty much automatic. The user is only in the loop by moving the slider back and forth. Okay, this cophonetic slider. So now you take this. Now you let the user refine it. Maybe user wants to make some more changes in the hierarchy, depending what he thinks the hierarchy should look like. And then in the end comes the labeling. Okay, the interior node labeling. Okay, so basically this is here, right? So, and you may wonder what these nodes are here, why they're colored like this. So I explain this to you here. So the node color basically is about the group quality, okay, measured by the Dunn index, determining how well this group really, really distinguish itself from the remaining data points. And the left part of this node here is the quality of the data space, and the right part is the quality in the semantic space. So when it's bluer, then it's better. It's more consistent in the semantic space, and then it means it's more quality in whatever space it is right now, right? So the right-hand side means it's the semantic space, the left-hand side means it's the data space. So here, this one here, that is landmark and restaurant, it's not bad, right? It's a little not as good in the semantic space, but pretty good in the data space, But as you go further out, you'll see that the consistency or the quality goes down, right? Because that's clear, because these clusters become bigger and bigger, right? There's more attributes in those clusters, and there's not going to be as much, there's not as much consistency anymore. The sort of, the clustering is not that good anymore. There's the clusters are not as dense anymore than they were before, right? So naturally the quality goes down. Okay, so let's see some examples, right? So when you go here, so I have to move this. So here's like data set King County. Oh, I didn't say this. The parent, the labeling of the parent is basically done also automatically, but can be assisted by the user. So the way we do this, basically, we figure out the pairing from the word the labeling of this parent node. We find it out by the word embedding space, right? Because after all, we have terms, right? We have these terms. For example, you have transportation, police, school, and hospital. You can see these terms in the word embedding space, or even in the high dimensional word embedding. And then you can find terms like service, where service is a hypernym, right? Service is a hypernym. Service basically the context that the service has, that the words that are around service are basically has a much bigger reach, right? That is affiliated with much more words, because it's a much more general term. And then basically these words are partially shared by the children, right? So police is a service, but police has also other words in them. And service contains police, and service also contains the word of school. Service also contains the word of hospital. Therefore, service makes a pretty good hypernym, right? And the user can correct that, right? The user can correct, well, maybe this is not a good hypernym. Maybe it should be a different one. And it turns out hypernym generation is actually a very difficult problem. Okay, it's actually not solved at all, right? So by having the user in a loop to critique these hypernyms as they're being generated, automatically, is actually a big plus, right? Actually, a user can go and say, well, I don't think it should be school. I think it should be something else. Or maybe, user can always do that, and the interface is pretty clear on that, right? So first, the user goes and creates a different hierarchy depending on what the user thinks matches together, and then labels this hierarchy. So oftentimes the user, I've seen this, user use the system, right? Oftentimes people start building like a parent node and they label it immediately, right? And then they build another parent node and label it immediately. So it goes sort of like one and one, right? So, and then they don't like the labeling, then they may move something around, right? So the user engaged, but it's always suggested by the system what a good labeling might be. When you look at this here in this interface that I showed you before, right? Here are some words that are suggested by the system, right? These are all words that could be possible labels for a parent, given a certain group of words as children, right? So the system will suggest a few words, and then the user can pick the ones that he likes, or he or she likes. Okay. So here's some examples of this. Okay, this is the King County housing data set, or the student performance data set, also lots of attributes, and the university data set. And when you sort of look at these, at these groupings here, grade 2, grade 3, grade 1 is grade, then higher education, nursery, school education, and then parent, mother, father education, it goes into education here, right? And then all of this is academic, and all of this is student, right? recreation, landmark, restaurant, park is recreation, service, transportation is service, value, condition, price, and score, right? So basically all of these sort of, this taxonomy is created with a human in the loop, right? The system tried to help using this containment measure that is given by the word space and from word embedding space, and then the user can always critique it and say, oh, I don't think this is really true, because hypernym is a really difficult problem, right? It's a really difficult problem because you don't really know what really goes together and what not, because there's always not enough information in the words themselves on the layout that it produces. And that I don't think that gets any better with BERT or Elmo or something like this. It's just ill-defined. It's just a partially defined problem, right? Where you just need a user in a loop who has a little more knowledge about, a little more common sense about the world. So this all is basically published. You can read about this more in this paper that was published in 2019 by Salman and myself. So let's go on and talk more about fairness and bias, where we also use words. So, okay, so let's talk about detect intersectional bias in word embeddings, okay? Because I told you, remember, let's go back to this slide here. There's algorithmic bias because these word embeddings, right, they're actually used to train classifiers. And these classifiers are used to read resumes or to read law documents or anything, right? Policy documents, right? They read them and then they come up with decisions that try to help. They're basically training a classifier. And then when a new person comes in with a particular resume or a particular, feature vector, then it goes to this classifier and gets rated based on how it was trained. So this can be very bad, right? If there's racial bias or gender bias or any kinds of bias in the data themselves, then women may just be discriminated based on that, right? Or black people may just be discriminated based on this, or intersectional people might get discriminated, like black females might be discriminated over white males, right? So this or black males, right? This can all happen, right? So the problem is really this, right? So you need to really come up with ways where you can remove this algorithmic bias that is imposed by the data that is being trained with, right? So you need to audit it basically. Okay, so so pretty much what subdomain of AI is affected? Pretty much everybody is affected by this. When you apply, if you're a student, you apply to a university that uses automatic transcript, automatic statement, automatic letter, auditing, letter calling, for example, where you try to, you write a beautiful statement, write a beautiful resume, write a beautiful, research statement, and have the subscript, this transcript, and then there's this automated system that tries to sort of make a first pass, right? Try to sort of maybe eliminate like 1/3 of the applicants that are clearly not good, that what the system thinks is not good, right? So you could be affected, or you may apply for a credit card and you may not get that credit card. You may get a loan, you may not get the loan, or you may not get an internet account of some sort. But anybody is affected by this sort of fairness of AI or bias of AI. Okay, so of course, minorities, underrepresented groups are the worst. Okay, worst, always the worst. Okay, in this, right? So the source of bias, right? The training data or the code developer is biased. Then the training data or the code developer itself may be biased. That can happen too. It's not unknown. So the human learns from books and the teacher. You might get to go to a school where the teacher is biased. You're biased. You may only watch certain TV programs. You're biased. You may only read certain books. You may be biased, right? So you are biased. You might be biased as well from what you read. And the same thing is with the algorithm, right? The algorithm reads data, and the algorithm is programmed by developers, right? The teacher is the developer, and the data is the books, right? So you learn. The algorithm learns from that, right? So now, good luck with arguing with the algorithm, right? Good luck with arguing with some humans, I guess. But anyway, but the nice thing here is you can work on this algorithm, right? You can help the algorithm. Humans oftentimes you can't really change them, right? It's very hard to change a human, or but it's easier, maybe easier to change an algorithm. And it's also nice because there's tools you can learn what an algorithm thinks, right? We have lots of work on that, right? Where you can sort of figure out why the algorithm thinks a certain way and how he thinks, or he or she thinks, right? So I give you like one example of this for particular word bias, right? So we also have work on regular data where we try to figure out in a sense how algorithms think, and then try to change the way they think, okay, which is explainable AI. So we have lots of work on this too, which is coming up. But let's talk about bias in word embeddings. Okay, so word embeddings, as I said, they can learn, exhibit social biases based on random race, gender, ethnicity, and so on, that are in the training data set itself. Okay, so they're oftentimes it turns out they're oftentimes manifested as stereotypes. Okay, it's like a stereotype, right? Whatever it is, right? There's like, I don't want to give any examples. I don't want to be biased by giving any biased example. But you probably know yourself, right? You see a particular person, and you impose a stereotype on that person. You sort of generalize out, right? Say this person has messy hair. Oh, I remember all people with messy hair are messy, or they can't be, or they make bad jokes, or something like this, right? You sort of, because you met a few people with messy hair that had that kind of abilities, right? So anyway, so basically bias is always a stereotype in some way or the other, okay? So, for example, males are disproportionately linked with career and math, while females are linked with family and arts. That is just a classic stereotype, okay, classic one, right? So, at least in the US, maybe in China, could be, maybe less, I don't know. I have a lot of female computer science students, so that may be a little different. But in any case, right? So existing literatures primarily focus on biases based on gender and race and age and religion. Okay, so this basically most biases are sort of based on that, right? But what my point in this work really is, together with Bhavya Gai, my PhD student, there is oftentimes biases that are compound, right? It's not just like being female, or just being black, or just being Muslim, right? It could be the female Muslim, or it could be the Asian female Muslim, if there's such a thing, right? That might have a bias, right? So you want to look at these sort of multiple social categorizations, right, where you mix them together, which is called intersectional bias. Okay, so black Muslim females could happen, right? So now they're really chastised. Right now you have a black and a Muslim and a female. Okay, you apply all these bias together, or maybe there's a bias specifically dedicated to this particular stereotype, right? So finding this out is basically the work here that we've been doing here. So let's quantify it a little bit, right? Let's see what it is, right? So let's see, there's the female words, she, her, herself, mother, lady. These are all words that usually associate with females. And then there's the words that associate with males, he, himself, father, man, him, right? So these are typical, no one would dispute that these are not male or female words, right? And then there's these other words that are not directly, particularly unmistakably associated with these particular, properties, being female or male. So nurse, waitress, actress, teacher, family, career, boss, warrior, actor. I mean, waitress by the word itself, it's female. Actress, it would be actor, right? So these are very, very female words to begin with. But teacher, not necessarily. Nurse, there's male nurse. The boss, why is the boss always male? The warrior, why is the warrior always male? There's armies that have female warriors, right? There's actor, okay, that is female, that is male, of course. Career, career is in the middle, but a little more to the male part, right? So this is, these are these words that are sort of affiliated with particular group of this gender attribute, right? But don't have to be, right? There's definitely male nurses, there's definitely male family, male family, people, right, that are the head of the family, right? The males are doing it, and the woman goes to work. That could be warriors. There's also female warriors. I think there's like a movie about this, and and the boss you can have a female boss, and females can have careers. Why not? So so basically we're looking at this sort of describe each word by a score. Okay, I think I have that here, right? So we try to find a score for a word, how biased a word is with respect to a particular one of these extremes, like female or male. Okay, so we want to find out, right? So, and we want to also express this not just for female, male, we also want to express in terms of race at the same time, or some other attribute that we're going to use. Okay, we're going to see that in a second. But now you see this, right? So neutral words should be in the middle, like here. Careers, kind of neutral in that corpus that we trained with, a little bit to the male side, and you can also notice these clusters are not like round, right? They have like a certain shape to them, which is not even convex. Okay, so now let's look at Google, right? So Google embedding projector is a pretty famous one, right? So it tries to put all these words in a word embedding, okay, and then but it can really only distinguish one type of bias, like for example, male versus female, okay, only a single word, okay, or black versus not black, stuff like this. And it doesn't really support any bias quantification algorithm really. So this is like the one that most people use to this Google projector, right? If you go out and download it, you can take all the word corpus and project it. It's massive because there's so many words, you'll find out. So you can filter it a little bit. So we're gonna go beyond this, right? So let's talk about design goals that we have. Okay. So we first want to figure out these word associations. So we want to given a word, say priest, the tool should help identify the different subgroups the word is associated to, along with the degree of association. Say priest is male, Christian, and old, right? Something we want to show that association. Okay, we want to be revealed to the user what this word is, what kind of connotation this word has. Then bias exploration, we want to be able to sort of go explore the words and see how they associate with different subgroups at the same time, like intersectional subgroups, not just male, but also black and Muslim females. Right? We want to see this. We want to be able to explore that, just have a word and see what is its bias. Okay, and then also see its synonyms and see its antonyms, how they behave. Right. Then bias types. I want to be able to specify my own bias, right? Like something that I don't know, right? That are not general. Like right now, I can only do gender, race, and religion and age, right? But I maybe want to do something that is not reported. Like there's no database on this. For example, political leaning or physical appearance or anything like this, right? So I want to be able to be exploring the bias on my own terms to learn about this, right? So that's another goal we have. And data volume, I should definitely be able to deal with lots of data, so it should not be just 60 points, it should be 1 million, so it should be this. So let's roll the drums and see our tool, which is basically this word bias tool that I'm gonna demo or show you a video of it. But first I'm gonna explain this interface to you. For those who a little more versed in visualization, they will immediately recognize there's a parallel coordinate interface here, okay, which is like a convenient interface if you want to show multiple attributes, right? And in this case, we're going to look at multiple attributes like gender, religion, race, age, economic. Okay, so we defined economic. That is not something that usually is used, but the other ones are pretty typical. So let's go one by one to this interface. Okay, so this is a control panel here, and this is this intersectional bias explorer. And so here, the first thing, so I'm going to run you through this, the way you would use this if you just got the tool and you want to do some work with it, right? So the first thing you have to do, if you have to define the groups, right? Because we're going to find groups, right? We want to we want to find words that associate with subgroups. I want to remember what I showed you for male and female, right? I want to give a definition of what male and female really means, like he, she, actor, whatever it is, some words that definitely go and describe that gender really well, right? You know, and I can find, actually you actually don't have to scratch your head and figure out where to find these words. There's actually databases for this that you can use. Okay, so you don't have to, dream them up by yourself. In the paper that we wrote, that I give you the title for later on, you can get sources for this. So there's basically a database for almost anything that defines like economic poor, economic rich, right? There are those words that define rich really well and define poor really well, and you would put them in here. Okay, so because you have to, then now you're training the system basically. Okay, so now, for rich, for example, these are the words that are found, rich, richer, richest, affluence, advantage, wealthy, costly, exorbitant, expensive, exquisite, and so on. And the poor ones, destitute, needy, impoverished, economical, inexpensive, ruined. These are all words for rich and poor, which you can find in the database, which I give you in the paper. So now let's go further and look at the bias level selector. Now remember, you have like millions of words, right? And you don't want to, maybe you only want to see the extremes, right? So this is a histogram of the words in a particular that are biased in one particular attribute or all, right? I can also do all, that basically a weighted average or just an average, okay? So on the tails are the words that are really, so the bar is basically a number of words that fit that bias score, okay? Which I'm showing here, right? This is the bias score. Basically the cosine distance of the center of one subgroup, and the word minus the cosine distance of the other subgroup, the distance of the other subgroup. This is the bias score, okay? And then basically what this here shows you now, I can filter it. I can say, well, let me only show the extreme words. I can also show the other tail, right? Let me only show the really biased words, right? Because to just sort of, make this parallel column display a little less cluttered, okay? So this is what I'm showing here. And then here I can use this brush slider where I can look more like, I can say like, hey, I want to only really see the extreme religious ones, right? Which are the Muslims, okay? Down here, the Christians, okay? It's always opposing, right? Muslim or Christian, okay? There's no Hindus or anything like this. So in this case, at least, I can also use Hindu here, but I have to describe it. And I can move this around as I please, okay? And then here I have this word list that basically tells me all the words that are represented here. Okay, here the words are here actually, and on this word axis. And there's some, I can go there and then click on them and then see them highlighted. I can also search for words that I might find interesting and see where they really fall here, if they're really extreme and how. Okay, so let me show you now this particular interface. I have a little video because it's probably best explained if I show you a video. So let me make sure I have the sound is up. The sound is up, okay. Then I think I should be able to run it now. So go to the beginning of it. I think I'm at the beginning. Okay. So let's watch.
This is the visual interface of word bias. Here each axis represents a particular sensitive attribute like gender, religion, race, age, etc. And either side of each axis encodes a particular subgroup. For example, the gender axis has female subgroup at the top and male subgroup at the bottom. Similarly,
Oh, what happened now? Oh, I don't think you can hear me anymore.
and either side of each axis encodes a particular subgroup. For example, the gender axis has female subgroup at the top and male subgroup at the bottom. Similarly, we have Islam here at the top and Christianity at the bottom. And each of these blue lines here represents a particular word. We can simply hover over any word to see how it associates with different subgroups. For example, here the word nuns has strong association with female, Christianity, white race, old age, and poor economic subgroups. If a word is not present on the word axis, we can simply go over here on the search box and we can search for a word that we want to see. So let's say we search for the word corrupt and we can simply click on the word and then the word appears on the word axis. Here you can see that the word corrupt has a strong male, black, and poor subgroup orientation. Now let's say we want to visualize the different sets of words. So what we can do is we can go over here on this histogram and we can select different words by brushing over the x-axis here. We can even go on and we can select all the words that are there in this tool. And now let's say we want to figure out which words are associated with the intersectional group black, young, poor. We can simply go over their respective ends and brush over these subgroups. The words that you're seeing here, struggle, hunger, uprising, all of these words strongly associate with each of these different categories, and hence these words are linked with the intersectional group poor, young, black. Now we can pick and choose different subgroups to see how different words associate with different subgroups. So let's say for the intersectional group white, old, rich, we see words like attractive, formal, desirable, castle, deserts, golfing, etc. Apart from the default set of axes, our tool provides the flexibility to add any new user-defined bias type. We can come over here and let's say we try to define a new axis titled weight, and it has two subgroups, let's say thin and heavy, and then we write down a set of words which define each of these subgroups. We click on add axes. Here we go, we have this new axis, right, as we intended.
Okay, that's the video, I think. So you can see like how this works. You know, you can just, there's a demo on the GitHub actually that you can use this yourself. And I give this.
This is the visual interface of what.
Okay, so that's the video. So we found some interesting, I just want to summarize a little bit what we found. Like these are these sort of words that are intersectional groups of, for example, poor, young, and black. These are the words we found. So poor, young, and black. Oftentimes, the associated words is disaster, struggle, tackle, chaos, woes, hunger, uprising, desperation. These are all very, very depressing words. And that's what these, you know, that's what these word embeddings have for young, poor, young, and black. You know, that is that's pretty bad. But now you have a white Christian female. You know, you got the romantic, nuns, virgin, Republicans. That's very interesting. Peachy, platonic, convent, a very clean, very good words, right? White Christian female. Then you got the young Christian males, career, dominant, brilliant. You know, it's really societal, right? You can really see society in it, right? In these words. When you read these words, then you kind of think about, you know, maybe not only one word, maybe more words that are appearing in this sentence. You don't even have to say who the person is that you're talking about. You just know it by the words, right? When you read like all these words together, formal, attractive, appealing, desirable, resort, seaside, golfing, cordial, bungalow, you'll think about a rich old white guy, right? You just think about him, right? Then it's very interesting just by looking at these words. You don't even have, I don't have to tell you what that person is. You can just see it in the words, right? By looking at this sort of array of words. It's fascinating, really fascinating. And so potential use cases, right? You can use it for auditing tool. For example, researchers could use this, what we find, and audit the word embedding so it doesn't have these biases, right? So these words don't always point at the rich white old guy, right? You move it, and we're actually working on something that will do this. This is like something we're working on and hopefully publish in shortly. So where we can edit these word embeddings, and then as an educational tool, it's just to read, right? You just use this tool and you can just learn about bias, right? You learn about the connotations that each word has. I think it's a great way for any type of education. And you know, it can also help law, linguistics, sociology to learn about the words. And we're actually working with sociologists and someone in law on the use of this. Okay, so this is the paper, and there's a GitHub on it, and you can get a demo, and you can even get the code there. Okay, it was a Kai paper this year. So some ongoing work that we use, try to do more languages, then visualize and debias for multiple sensitive groups simultaneously, or the debiasing, basically do the debiasing of it. Right now we only detected it, but debiasing too. Then use this tool for augmented writing tool for groups with special needs or any kind of people. So for example, we developed this called this Fluent tool, which we recently published for people who stutter, which was one of the tools that we used this for, was published at ACM CSIG-VIS 21. And just central algorithmic bias identification mitigation in general, right? So we actually, I'm working a lot on this, and there's a lot of research I'm doing right now on this kind of topic. So more papers hopefully will come out soon. So just want to end this by thanking PhD students that worked on this, by Olimet, Bavia, Naimul, and Salman, multiple funding agencies. Down here, you just sort of see a little bit my themes of research, make things transparent, use visual interfaces to boost it, make it accountable, let the human be in charge, and the human can be held accountable. He feels accountable, make it multidisciplinary, so involve lots of different types of experts to stakeholders to sort of arrive at a common consensus, and then trust. By inversing the human in a loop, you can probably get a lot more trust into the algorithmic systems, right? So because humans sort of know how it works and what is behind the scene, they're able to modify it and edit it. They probably trust it a lot more after that. So that's pretty much what I have to present. Hope it was informative. So.
Oh, okay. So thanks for your presentation. So we got lots of questions for your talk. So, okay, I first ask my questions because I have a question about related to your word bias work. Can you show me go a little bit back about the slides?
Which one?
The one with pair coordinates.
Oh yeah, okay.
Yeah. See, okay. Maybe next one.
Oh, this one. Okay.
Yeah, this one. So I'm not sure why you choose pair coordinates, because for me, all this data looks like categorical data, not a numerical, right? It's not continuous. It's just categorical.
Oh,
so yeah,
it is continuous. The score is continuous. The score.
Oh, the scores is continuous.
The score is continuous. Yeah.
But for me, it's just two categories, right? So it's like one male, one female. So
yeah, right. These are the extremes. No, this is the gender, this is the female. But each word has a numerical score. It tends to be more female or tends to be more male, or this word tends to be more Muslim or more Christian. So this is it's a numerical score.
Okay.
You can remember, look at some lines here, right there, like go here, some in the middle, right? So some words are neutral, some words are completely neutral, right? They can't, they're not female or male, right? Child is like, could be female or male, right? Or human could be male or female, you don't know, right? There's a lot of neutral words, and actually we train the system with neutral words as well.
Okay, so we got a question from the audience. So, okay, first one is, when measuring the bias distribution, should the group categories be independent to each other, such as gender, age? This group categoricals may not be independent in the data. Does it contribute to the algorithm bias? I mean,
yeah, we consider them to be independent, right? Of course, there are joint relationships, which is actually brought out by this, right? You can be male. Yeah, there are actually also intersexual biases that are very, very specialized. I forget now what they were. That are actually not. They cannot be composed by just, right now we're just linearly joining them together, right? But there are also some, I forget what the word was. There's some biases that are just really by only by bringing the four terms together, the biases comes out, but not independently, that wouldn't come out. I just forget what it is. But we assume it's, it's kind of an independent kind of thing. Like we look at they can be, we don't look at that. We bring them together in this sort of composition interface. Of course, they can be they can be dependent, and we bring this out, right? If there's a line that goes to the males and to the Christian, right, at the same time, then they probably are dependent. But this is just on a word basis, not on the overall data distribution.
Okay. There's another audience said, oh, okay, sorry, I missed the part about solving the synonym problem. Can you explain it again? If true, why not split the question words in the data pre-processing stage? For example, split the jungle into jungle 1 and jungle 2, and the former being related to car and the latter related to wild cat, something like that.
So what is this referring to? To the debiasing or to the subspace paper?
The example is just when you start your talk, you place a problem about jungle, right? Jungle could be a car or could be an animal, right?
Jaguar. Okay. Yeah.
Jaguar.
Yeah,
So
right.
the audience will ask,
right.
Why not split it before that? Yeah.
Yes. That is an idea I had myself a long time ago. But then, and I actually thought about doing it. But then there's BERT, like all these more advanced ones, they already do this, right? BERT and Elmo, these more advanced word embedding, they already distinguish the cat from the Jaguar from the car Jaguar, right? They already do that. But yeah, you could, and by using this metadata that we have, we can guide it a little more what we really mean by Jaguar, right? By having this meta sentence, we tune the layout more towards that, right? But then maybe it's going to be undone by the big data corpus. But that's a good idea. Yes, exactly. It's a great idea to split them. I had that idea myself, but then the BERT and so on came along, then we never pursued it.
Okay. Another question. Can you explain a bit more about correlation embedding? Does it use the distance between the semantic measures?
No, the correlation embedding is based on the attribute from the data, right? You take like two columns, and you figure out what the correlation among these two columns are, right? And you
so in this measure is on the semantic.
The semantic subspace, yeah, and any of these, right? In this one here, right? I think this is probably what the question was about. This one, right? The data space, that uses correlation distance. We create a distance matrix, right? The distance matrix based on correlation, and then we lay it out like this.
Oh,
with an MDS and with MDS or metric, non-metric MDS.
Okay. Oh, I have a question about this hierarchical structure. I really wonder the node on the same level, is there some ordering or just random?
There's no ordering on the same level. I mean,
so
you mean within here, within just
it's ordered or not?
No, there's no ordering. No.
Okay. But for large graph, for example, you have lots of words, right? You have to order in some way, right? It's maybe better.
I mean, here we have this.
Yeah, because the example you showed just like 20 nodes, 30 nodes, something like that, right? So, but if you show like 30,000 nodes, then you have to order in some way.
Then you might want to, but then you would probably use some sort of hierarchy visualization method, right? Where you sort of zoom into one particular tree, subtree, and then the other one is collapsed, right?
There's some
we don't order it by grade. You can see grade 2, grade 3, grade 1, so it's not ordered.
It's not ordered, but okay. For the nodes, I mean, for the tree, is there a minimum number or maximum number for the how many nodes you have, or how many children you have, something like that?
Well, the children is the attributes in the data set.
Is there a maximum number or not?
No. I mean, we didn't try for more than, I think, 60 attributes. There's no real true limit on. I mean, it's just a visualization problem, right? But not really an algorithmic problem. It can have more nodes, but Yeah, we just didn't have more bigger data sets that have more, that we didn't have more data sets that had more nodes. There's one we know about that have 120 nodes, but there's just not a lot of data sets that have really, once you go out to the imaging, right, images or genomes, you have higher dimensional data sets. But if you have data sets with regular attribute names, usually there's just not a lot of data sets out there that have more than 60 attributes in them. Unless you join some, then you have maybe more.
Okay, so a question from the audience. It seems like the bias distribution in the examples are always unimodal. Is this always true in the real world analysis? What should be updated for the multimodal distributions?
Or you mean you always need a model for the bias? Well, we're looking at algorithmic bias, and the algorithm is usually a model. But we could, but we also have data set like where humans made decisions, right? For example, which usually the models are trained by real life data, right? So you just train a model with this, but we can detect bias in the data itself, right? We don't need a model to produce the bias, right? We can look at the data itself without a model. We just get a collection of points, right? A collection of words or a collection of predictors from a real human. We can see how humans are, how much is a systemic bias, historical bias in the humans. There's no model needed for that. But nowadays it's become more attractive because now people train models to replace the humans, right? So now and now you can change the model, right? Before you couldn't really change the human because you have a guy in your office, right? Or your guy administrator in your school or whatever. You cannot tell that person, okay, now you have to do different, right? He'll say, well, I've been doing this for 20 years like this. I'm doing it like this for the next 10, right? But now you have a computer doing the decision. Now you have a real chance to improve things, to improve the world, because now you can change the algorithm, right? And you can. It's a much easier thing, right? You don't have to change someone's mind. All you have to do is write a different. All you have to do is program the program different. The computer doesn't care. It's easily programmed. It doesn't resist that intervention, right? So.
Okay. I think this is all the questions, and because the time is up now, so okay. So let's thanks Professor Klaus Mueller for this amazing talk, and also thanks for Professor Wei Zeng, Professor Cheng for helping me to organize this talk. And thanks so much.
Okay, thanks for having me.
Okay.
Nice to see you again, Shenghui.
Yeah, nice to see you.
Okay, bye-bye. Bye-bye, everyone. Bye, thank you.
感谢大家的那个支持吧。然后我们经过了半年的努力，我们已经把我们的可视化与可视分析这个国际学术报告会议，然后进行了一个半年的活动吧，然后做一个简单的总结。然后这个是我们的邀请的专家，当然这里边包括已经完成的是红色的点儿，还有没有完成的是就是说2022年的上半年的是这个灰色的点儿，也就是说我们即将邀请的，我们已经完成了7位这个国际的教授的报告，然后在2022年的上半年我们还有14位的报告。所以我们这个是相当于是2022年上半年的报告的一个预报吧。我们这些专家也是世界各地，从这个欧洲、亚洲、美洲，我们都包括了。这是我们这个报告的情况。所以我们现在已经完成了这个2022年上半年的报告的安排。这是我们的一个讲者的信息。那我们的这个支持者的信息包括了我们现在应该是有16所学校的支持，包括了现在已经完成的和后边还这个没有完成的。 是包括了这么多学校，我就不念这个 list 了。感谢各位老师的这个大力支持。在2022年的上半年，也希望各位老师这个能够继续大力支持，然后完成我们上半年的报告。这是我们工作组的成员的情况，然后给大家简单介绍一下。那袁小茹老师是我们的专委会主任，也是这个活动的发起人，然后一直在帮我们指导工作，包括刚才那第一张图片，我原来做的很丑，袁老师帮着做的一张很漂亮的图片。然后这是曾伟老师是负责我们的这个新闻稿的撰写，陶军老师是负责我们整个这个工作的联系，这个国外的讲者的这样一个工作，包括签一些这个是否可以放视频的协议等等。徐瑞歌老师负责帮着联系国外的一些艺术领域的专家，然后于凌云老师是我们这个微信的公众号的这个负责人，然后刘乐老师是我们这个网站的负责人，及时的把网站的信息更新。然后张萌老师是我们的艺术设计，也就是说我们所有的 poster， 包括这个背景，包括我们的背景墙的设计，都是张萌老师来负责的。然后魏倩茹老师是我们专委会的秘书，整个活动有时候大家跟不上的时候，都是靠魏倩茹老师来帮我们 push 的，完成了整个工作。我们还有这个3位志愿者，李佳阳同学、这个苏坤华同学和邵林丹同学。还有一位同学的照片没发给我，所以这里只有3位同学的照片，他们做了大量的工作，包括前期的准备以及这个线上的帮着这个转播等等的工作。感谢3位同学和几位老师的努力。这是我们明年的一个预报。所以我们一共有明年从1月6号开始到7月14号 China CSIG-VIS 之前，我们一共有14位讲者，仍然是每2个周一次，都是周4。当然时间可能是早晨的9点或者是晚上的19点，这2个时间是因为我们有时差，所以不一定是哪一个时间，但是基本上就固定在这2个时间，9点或者是晚上的7点、19点这2个时间。然后我们邀请的这14位讲者也都是我们可视化领域各个方向的这个比较做的大牛专家，所以希望也希望能给大家带来一些这个比较好的精彩的报告。好，这个我要讲的就这么多了。然后我们第一次报告，2022年第一次报告在1月6号，欢迎大家过来收听陈建老师的报告。这是一个简单的介绍吧，预告。然后感谢大家这半年的支持。我们2022年上半年见。好，谢谢大家。